computer, make sure I'm recording. I am indeed recording since I forgot to record my CCNA 3 class last week when I was at home. Be aware when you do a lab that's using the serial interfaces, it takes a good while for the serial interfaces to come up on these routers. So give it time to come up and start running. Otherwise, you will boot them up and you'll look and you'll be like, well, there are no serial interfaces. Well, it takes them a good 8 to 10 minutes, it seems like, to get up and running and to be visible. I do want to go over this lab here in just a second, but let's go ahead and start with discussing EIGRP. Now, it used to be back in the day, EIGRP was a big part of the CCNA. How many of you remember that? How many of you went through when the EIGRP was actually in the CCNA? Brian, did you and Eddie go through during those times?
Oh yeah.
Okay.
The first couple of times I took CCNA, it was on there.
Okay.
I was kind of surprised that they took it out, but with everyone moving to OSPF, well, not everybody, but
right,
the vast majority of people moving to OSPF.
and I think that's a big reason why. Obviously, I'm kind of shocked too, though, because they did make EIGRP an open standard. So I was like, well, if it's an open standard, let's, I don't know why you would take it out, but they did. They took it out and moved it all the way up here into CCNP, and we do discuss it in Encore. Obviously, we'll do a real quick overview again here of EIGRP on just in case for some reason some of your classmates are not familiar with it. EIGRP is a distance vector routing protocol. Now, many times you'll see it for years and years, they call it a hybrid protocol. It's not. It's a distance vector protocol with link state traits. That's the best way to really define it. It still is a distance vector routing protocol at its core. However, it does some things like a link state, and that is not Notepad, but Notepad. It is a distance vector routing protocol. All right, which means it is an interior gateway protocol, or an IGP. That means it runs inside of an autonomous system. It has some very link state characteristics. One is obviously triggered updates. So it will send only updates when a change occurs. It has bounded updates also. So in other words, they're only going to go to those that it will affect, and that's using the autonomous system concept. It also has inside of it the ability to support VLSM, which is pretty common, variable link subnet masking. And it is a routing protocol that originally was Cisco proprietary, but it is not anymore. It is now an open standard. It's an open standard. It has not been adopted by very many other vendors, but it is an open standard, so it can run on different equipment. It is a little different because it's something that using some of those link state type protocols, it has multiple tables. So it has an adjacency or neighbor table. So basically a neighbor table. It has a neighbor table or an adjacency. Adjacency table. It has a topology table. And then it takes information out of that topology table and eventually dumps it into the route table. So as a routing table. It uses a dual algorithm, which is a diffusing update algorithm, and it is going to be able to hold in that topology table both the best route and routes that reach what are called a feasibility condition. And we'll talk about the feasibility condition when we get there, but it's basically a route that can stay in the topology table as a possible backup route to immediately be put into the route table in case the primary route, which is called a successor, fails. We're going to go over some of the fundamentals, look at some configuration modes, and then talk about the path calculation and some places you can get yourself in trouble if you're not careful. So EIGRP, it actually was built out of IGRP. And so IGRP was another protocol that's now no longer in existence, but it is built basically on that. It does have a hop count for up to 255 hops, has rapid convergence features, and again, that's those triggered updates. And it can do unequal cost load balancing using a thing called variance. And we'll talk about variance when we get there. But it is to be used within an autonomous system. Now, you can actually break the EIGRP groups into different autonomous systems by using a different number. Now, in the configuration, it says router EIGRP autonomous system number. That's really not an autonomous system number in the way we think of it in terms of an autonomous system with IETF or being registered for BGP. It's more just a grouping of routers together that are going to share information. It can support both IPv4 and IPv6 through different protocol independent modules. So it's able to actually run any layer 3 routing protocol that's there. Now, some of the terminology we need to talk about. The very first piece of terminology is what is called a successor. So as you look here in this example, all right, let me kind of see if I can get this a little bit smaller here. This example here, we have what's called the successor route. Well, inside of EIGRP, the successor route is basically just the best route, okay, the best route to a destination. And then there's an item called a feasible successor. Now, what does that mean? That means it's an alternate route that meets the feasibility condition. And what is feasibility condition? It means that the reported distance is less than the advertised distance, okay, or the best distance. That's the feasibility condition, or FC. FC equals when a router's reported distance is less than feasible distance, total route cost. Now, what we've got here, let's take a peek. And that is, at first, this is kind of a hard concept to understand, but let's look at our example we've got here. We've got this network, and we've obviously got multiple routes to get to the 210.440 destination. Our particular best route is the route that consists of 256 plus 256 plus 2816. All right, so we've got, let me go in here and grab me a little calculator here because I am math. 2816 plus 256 plus 256, which would be 3328. So our best possible route is 3328. Okay, so our successor route is 3328. Now you see why that is true, because the other routes, by the way, that's the route from R1 to R3 to R4. So that is our route, R1, R3, R4. The other routes, by the way, if you look at them, R1 to R2 to R4 has a distance of, take a peek here, 2816 plus 2560 plus 2560, which equals 7,936. All right, that's that one. And then the route from, and there are multiple routes here. We got R1, R2, R3, R4. Okay, that's going to be fairly large also. So 2560 plus 256 plus 256 plus 2816 for 5,888. And then, of course, we have another route, which is R1 to R4, which actually ends up being 2560 plus 2816 for 5,376. Okay, so we do say our best route is this one with a cost, a metric of, not a cost, because cost is the metric for OSPF, but the metric of 3328. All right. Now, in order to meet the feasibility condition, this router's reported distance to R4 must be less than the feasible distance for the best route. So if we look here, okay, So the reported distance for R1 going across this top route would be 2560. 2560 is less than 3328, which means that if it were to use the route from R1 to R4, there's no way, okay, that it could go through here because, again, remember, feasibility condition equals my reported distance is 2560, and that is less than the best route of 3328. So if my reported distance is this, there's no possible way I am going through here in order to get to the destination. Because if I was going across the best route, it would have to be some number above 3328. That is why this route does not meet the feasibility condition, because if you took 2560 and 2560, it's over 5,000, which is more than this. And the other route down here would be 2560 plus 256 plus 256, which is again greater than 3328. So the only route that can be a feasible successor is R1 to R4. Now, the good news is these other routes are available as backup routes. They're just not a feasible successor. So they won't be in the topology table in order to take and able to take over quickly. You would have to actually go into it, and the dual algorithm would have to be run, and you'd have to find a new route. So if the route from R1 to R3 to R4 failed, and the route going from R1 to R4 failed, it would use R1, R2 to R4, but it would have to go back through the diffusion algorithm in order to do that. Now, this is one of the main concepts in EIGRP. Does that make sense? If you don't have a mic and you have a question, I've got chat open also. If you want to come off mute, you can do that. It took me a long time for this to make any sense until I realized as long as my reported distance is less than this best path, there's no way I went through this path because it's less than that. And if I go through this path, so it can't be looping through the best path in order to get there. It'd be impossible. And that's the feasibility condition. It's also why the feasible successor is important, because if it's in the routing table, or excuse me, in the topology table, and your main route goes down, within milliseconds, your feasible successor route will become active, which is one of the reasons why EIGRP is a very fast protocol. All right. So successor route is our best route. The successor is the next top router for the successor route. In this case, it's R3 in our particular thing. Feasible distance is the lowest metric path to a destination. Reported distance is a distance reported by router to reach a prefix. So that's how you get to the prefix. R3 advertised it with RD at 3072. R4 advertised it with 2816. So we got 2816. We got those. Feasibility condition is when you are a loop-free path that meets the feasibility condition, or the feasibility. I kind of call it a not an algorithm, but a well, it is kind of an algorithm, but feasibility metric or condition. Feasible successor is that route that satisfies feasibility condition is marked as a backup route. You will see that here inside of the topology table. If you do a show IP EIGRP topology, we see all of our routes. We see that our feasible distance is 3328. The reported distance is 2816. So that is in the route table, or excuse me, topology table. By the way, this will not even show up if it doesn't meet the feasibility condition. So if it does not meet the feasibility condition, it's not going to show up in this topology table by default. You would only see the successor. So in our particular network, the 1012, or in this network that's shown in this topology table, the 10.12.1.0 network does not have any other routes that meet the feasibility condition. There's no feasible successor. All right. This is an example of a route that is actually automatically doing load balancing. You'll see there's two successors because they have the exact same metric and reported distance. So feasible distance and reported distance, which gives you automatically will do load balancing. And then you got down here, you're seeing we've got one successor, but there are 2 items in the topology table, which means the second one meets the feasibility condition. So each one of these routes to 34, 24, and 4.4, each has a feasible successor. If you wanted to see all links in the topology table, use the command all links, and it would show you there could be more links to the 10.12.1.0 network. They're not being shown in this particular output because we're not asking it to show anything except for successors and feasible successors. You want to see everything, you need to do the all links command on the topology. Okay. So, like a OSPF, EIGRP doesn't do periodic network, periodic advertisements of all of its routing table information. It actually does a triggered update. It also does a neighbor relationship in order to track with what neighbors are where and to form that adjacency. And here are the 5 different packet types used by EIGRP. And we will see here that it is, by the way, EIGRP has its own protocol number, which is 88. And when possible, we'll always use multicast using 224.0.0.10. And it's, let's see, I think it's FF02::10 for IPv6. But EIGRP has what's called a reliable transport protocol, has its own transport layer protocol, and that is so it can be protocol independent. And you'll notice that in our packet types here, we have hello, which is obviously used for our neighbor discovery. Request, trying to get information about specific from a specific neighbor. An update is transmitting that information to your neighbors. Query is if you're asking for another path during convergence. So let's say a path goes down or you need to know about a particular network, you could send a query and then you would get a reply. So these are the 5 different types of EIGRP packets. Less than OSPF, as we will learn and have learned, OSPF has more. So we're forming our neighbor relationships. Now, in order to form a neighbor relationship, a couple things have to match. One is your autonomous system number has to match. Your primary subnet has to match. And your metric values, your K values. We'll talk about those in a minute, but the items that form the basis for your metric must match. Your K values are going to match. So if you ever change your K values, you have to change them in your entire network, or at least between your every neighbor that you're going to change it on. But you really need to change it on every individual router if you're going to change K values at all. And then if you do have authentication set up, then authentication must also be enabled on both sides. There are 2 main ways to do configuration. One is the classic mode, and the other is a mode called named mode. So with classic mode, you go out, most configuration takes place inside the EIGRP process, but not all of them. Sometimes you have to go out to the interface and do some things. It is can be a little more complex, and it's also just going away. So it's the other bad thing about classic configuration mode we're going to learn is as soon as you configure classic configuration mode, you're going to be using what is called the classic metrics. Classic metrics for EIGRP see any, okay, so any, let's go and do this. Classic metrics pretty much see anything, any link that is 10 gigabits or faster as the same speed. Okay, so it assigns the same metric value to them. So that's not a good thing. And by default, if you use classic mode, you're going to be running classic metrics. If you use named mode, you get what is called the wide metrics. And this can handle faster links. And if I read correctly, and I think I did today, it's 455 gigabits per second. It's the fastest link it can handle with wide mode, which will meet most of our needs. You know, it's pretty much. Real quick, how many of you knew that Wi-Fi 7 was ratified in early January? Anybody hear about that? I actually just read it out yesterday myself. But yeah, there's a new Wi-Fi 7 mode that's out there.
Heard of it, but didn't know it was ratified.
Yeah, it actually was, it is ratified. It is using the 6 gigahertz band, and it's not actually available everywhere. It's available in US, I think Australia, Europe, a couple other places, but I thought that was pretty interesting.
So
Um,
46 gigs, right?
I think so, yeah.
That's a theoretical throughput.
Theoretical, correct.
Yeah, if you're standing underneath of it and you have enough power in your NIC card to do it, you might
Might
get
get
somewhere
pushed,
near that.
yeah. And you'll probably have, you know, a brain tumor within 2 minutes. I'm just kidding. It is that the 6 gigahertz. The crazy thing is, even with Wi-Fi 7, there's so few people even using Wi-Fi 6 now. It's like these standards are getting so far ahead that it's crazy. I mean, it is something you want, but I mean, you can barely afford in your house a set of Wi-Fi 6 extenders and routers. I think the Orbi gear is like $1,000 for 3 of them. So I don't know. It's a good standard. I think it will obviously roll out, but it will be rolled out more than likely first on phones and things that people change every 2 months, it seems like.
It's
You
got
know,
some crazy channel bandwidth. Like it's like 320 megahertz or something.
yeah,
Yeah.
got some crazy jumping like MIMO stuff it can do.
Yeah.
But you know, if I was in an environment, so let's imagine I lived in an apartment complex and I was having struggles with interference, I'd probably go buy me one because you're probably going to be the only person in the area with one for a little while anyway, and then maybe you'd stay ahead of the game. But um, the cows in the field over here I'm looking at, or actually I'm just looking at nothing but trees. I don't have to worry too much about interference. Now, named mode, it allows you to put everything in a single area. It does support multiple different features and future developments, and it is the path forward. It does support virtual routing and forwarding instances. So it does support VRF, and then it is pretty clear in their configuration. You have your address families, IPv4, IPv6. You have interfaces inside of there. You can set default information for interfaces underneath your named modes. Then you can also, like, if you want passive interface default, you can do that by doing AF default and then our interface default and then taking interfaces out of that. For the most part, we are going to be working with named mode in the future. We do have a lab. We're going to do both here, but just be aware that we're going to be working with named mode in the future. Here's an example of network statements. Just a couple ways you can do it. You can configure it with wildcard mask if you want to. You can do it with regular mask if you want to. I use the regular mask and try to get as close as possible to what is there. What you can actually do is by using different types of wildcard mask. That's not bad there. Eddie just looked and found Linksys 7 tri-band mesh 3-pack for $7.99. Honestly, that's not bad for 7. I don't know how good Linksys one is, but still. Especially when you consider, if you look up the Orbi stuff, the Orbi, even Wi-Fi 6 Orbi is almost $1,000 for 3. Last time I looked at it. Let's jump over real quick. I'm gonna go and look. Now, by the way, here it is again. This is classic configuration at the top where you go in router EIGRP autonomous system number, put in your statements, and then go down the bottom here is named. By the way, one can be using classic, one router using classic, one using named. There's only one problem there though. The classic router is going to be running classic metrics. The named is going to be using wide metrics. So if you get a mix match of wide and classic, you can really end up with some weird routing stuff going on. So I suggest either do all one or the other. And if your environment needs the wide metrics, then you got to do all named everywhere. Okay. So let's jump out here just a second. Let me jump over to this because I want to show y'all a couple things. First off, let's get into router 1. All right. So I have still not completed all of these for you, and I apologize. I'm useless What can I say? But I do have for lab 212 a starting config. So I'm gonna grab router 1 starting config, do a control. So I just open it up, do a control A, do a control C, go in here and go paste the terminal, control B, paste, jump over to R2, go to R2, open it up, go over here, control A, control C, R2. You know what? I think I forgot to do config T. I did, like a doofus. Okay, hold on a minute. Let's try this again. Control C. That router's locked up now because it's like, what have you done to me? You do have to go into global config, otherwise it will not work. So let me go to router 2 over here, control C. And let's paste the terminal. B. Make sure I've got the right one. Yep, that is correct. There we go. Okay. So let's try again over here. If you don't do config T, it ain't gonna paste, folks. Just for the record. Control A, control. Oh, wait. See. I'm having all kind of trouble hitting the right keys today. Okay. Let's go to R3. And I am still working to get y'all all these done for you. I hope some of you are planning to come to our event next week, our ASC ITC event up at Isothermal Community College. It's kind of snuck up on us, I'll be quite honest with you. I was quite shocked to realize I was sitting there this morning and I was in the shower and I was like, holy moly, it's the 26th. All right, ooh, our event's next week. So it's going to be nothing else. Hopefully we'll get y'all configured or all CCST networking and security. That's our goal. One of our big goals, and we'll feed you. Obviously, we will feed you. We'll let you go hungry. We got actually a good fajita lunch we're having. All right, so I'm getting ready to have all this pasted in. And the main thing I want to do here, do a show IP and brief. Let's make sure our interfaces came up. And they did. All right. So looking at our lab, one of the things we're going to do is we've got this configuration here, and we're going to configure EIGRP, on R1, R2, R3, and D1. We are just going to do it on R1 and R2 to begin, and then we will move on from there. But we're going to go ahead and do first, we're going to use classic mode on R2. So just let me pull these out here, and I'll pull out R2. Let me open this one, undock it. And we'll put this on this side, and then I'll come over here and grab this. Okay, so on R2, we're going to do classic mode. So very simple. We'll go in here and we'll do go into global config, router EIGRP 27. That's our autonomous system number. And we will set our router ID, which is just like OSPF and other. It's a 32-bit ID that is used inside of hello packets to identify the particular router. And then we're going to do our network command. So we're going to do network, and in this case they use 10.0.0.0, and they did a 255.224.0 to get all the 10 networks on it. And let's see, do we need? I'm trying to remember if we got to do. Yep. So now we can go in here and look and do a show IP OSPF. EIGRP, we got OSPF on the brain interfaces. You'll see that we're running on gig 00 and 001, we're running EIGRP. All right. Now we're going to go over to R1 and we're going to use named configuration. So we're going to go route config T, router EIGRP. We're going to give it a name. So instead of putting autonomous system number, we'll give it a name. We'll do basic dash EIGRP dash lab. And now you'll notice we're in router configuration mode. We'll go in our address family, IPv4, and then we'll do IPv4 autonomous system 27. So now we're going to configure this. We got to set our router ID. Router ID of 1.1.1.1. And then we're going to do our network statements. So let's see, network 10.0.0. That's 10.0.12.0. 0. Let's see, 172.16. 172.16. 1.0. And then 192.168. There's an 8. 9. 6.1.0. Okay, so we got those. And that should be it. Now we're going to exit. Do show IP EIGRP interfaces. We should see we're running on gig 01 and 1.1, 1.2. So our sub interfaces, we're running them on there. And now we're going to go real quickly over to R3 and do the same thing. So config T router EIGRP basic. Actually, I'm going to call it basic because I'm lazy. Doesn't have to say the same name at all, y'all. So address family IPv4 autonomous system 27. So we're all in the same autonomous system. EIGRP router ID. Let's see, on 3 it was 3.3.3.3, 3.3.3. And then we need to go and find our network statements for 3. So let's go and look. So we got network 10.0.23.0. 0. And then we do network 172.16.1. 72.16.1. And then 3.0 for 168.8. All right, so we're done with that. And let's jump down and do our.
I'll put when you put in the autonomous system 27.
Yeah.
There was right before that it said unicast, and you didn't put that in there. So is that needed or not?
You can use it, but yeah, I should have been putting it in. You don't have to put it in, but it should have. It actually do unicast and multicast, but it'll do both. I'm basically just telling it to run both unicast and broadcast based, basically. Let's go back.
Does it default to unicast?
It does not. Defaults does accepting both. So let's do.
Okay.
EIGRP. I've called this one basic. Okay. Let's do address family IPv4. And so there you can see it's multicast, unicast. It will actually support both by not doing either, not doing one. Okay. So it will work though. It'll work perfectly fine without that. I just missed it. I didn't see that. In fact, I did lab earlier today and used it and it worked perfectly fine. Other than the error we're getting ready to find. And then D2. Need D2 to have big T. Router EIGRP basic. Family IPv4. I'm gonna keep it the same since I've been messing up on the others. I don't want to. Let's do EIGRP router ID. This is 132.132.132.132, which is weird, but it is what it is. And we got to do our D2 interfaces. So network, our networks 172.16.1.0. Oops, 13.0. All right, so now we should be at the point where we can go back to R1 and take a peek at its routing table and its information. And this is where I run into that problem, which I'm thinking should still be an issue, but let's check. Because I actually saw where I did something a little bit different on this one than I did on one I did earlier, but it'll work. So let's do a show IP EIGRP, show IP route, EIGRP, pipe. I'm just going to do that. Let's actually do that, see what we get. So here's our route. So we got a route to 3.0, we got a route to 23.0, we got a route to 16.13.0. Everything's good so far. Okay. So it gave me the exact same thing without doing begin gateway. So, but we've got the same thing we got here. But now let's do a show, and I want to just do a show IP EIGRP topology. Okay. Now notice we have here underneath each one of these a single successor. Now let's do all links. Let's take a peek. For some reason, we're not getting our secondary link for this one. Or our secondary link for 3.0. We're getting it via gig 0.0, but not getting it through the other one. R3 and D2, which I did. All right, so that's right. Yeah, you got that. You got that. All right, so we should be able to ping from PC1 to 3.1. So let's try that. See if we got that going. Yep. By the way, this is set up to get its IP address via DHCP. So ping 192.168.3.1. Yep, no problem. So we got that working. All right. Let's try it again. Just see. Maybe it'll take a little bit. Nope, we're not getting that for some reason. We should have been seeing. I'm not getting anything through our. Yeah, we are. We're getting that one. So we're getting some through gigabit 1.0 through gigabit 1.2, which is correct. All right, so let's do this. Show IP probe. Let's make sure I put in the right thing. I may be missing a 10.0.12.0 R1 10.0.12.0 correct. 1.7.16.1.0 correct. 192.168.1.0 correct. Go to R2. We show IP probe. Okay, that's correct. That's got both those networks. To show IP probe. Make sure I got these. 10.0.23, 10. 172.16.1. Ah, there it is. 13.0, not 1.0. Blue bar. Okay. No net 172.16.1.0. Oh. One 172.16.13.0. Please. All right. There we go. Now let's see if we get our links. Not yet. Make sure I can goop something up here. To show. Oh. I was typing pretty quick, so there's a good chance I messed something up. Yep, right there I did it again. I did 1.0 and no, that's correct. 1.0 and 13.0. That is correct. So it should. Oh, there they go. All right, so we're getting at least, yeah, bingo. Now, all right, here's where things went sideways. If you did the lab right and didn't screw up like I did, this is where it actually went sideways. So we're looking at item D. We do the all links, and it looks like we should have 2 successors to 3.0. We do not. Take a look at what we've got. We've only got 1 successor route. So I started looking around and thinking, why am I having this issue and what's the problem? Well, one of the first things I did was show interface, show IP EIGRP interface, and I was going to go look at that interface. So gig 000, and it's up and running. Then I just said, let's do a show int G000.1 or 1.1. Okay, so this is a gigabit link. All right, it looks like everything's good there. But look what happened when I did this. All right, it's a gigabit link. So this is a gigabit link, but look at what speed it's running at. So it's a gigabit 00, but it is running at 100 megabits per second. Now, if we had real gear connected together without our control switches in the middle, R1's gig 000 would be connected directly to gig 00 on R2. We have realized that there's actually a config mistake in the actual control switches that can support a CCNP pod, and we didn't think about this. We have, in actuality, if you look at the way these things are set up, this link actually doesn't go directly to R2. It actually goes into a control switch, and that control switch port gets set to a VLAN to make it look like R1 and R2 are connected by a cable when they are not. That is so that when you boot up a pod inside of NetLabs, it can move around and you can move things and change connections. Well, if that back-end control switch is not a gigabit switch, you're going to have 100 megabits per second. And what happens is it will not then give you the correct information because it doesn't think the speeds are correct. All right. Now, what I could do to fix this is I could go all the way down through this pathway down here and make all of these fast Ethernet links. Okay. So I could take gig 001.1, gig 001.2, force it to speed duplex of 100, and it should make it have 2 successors. Let's try that. Okay. So we got gig 1011, gig 101 on D1. So let's go to D1 first. And let's go to config P int G1011. And let's go no negotiation. Okay, so it doesn't have that. So we're going to speed 100 duplex full. Okay. And then we're going to go to int G101. We're going to go to speed 100 duplex full. Okay. Now we'll go over to D2. Go to G10 int G1011 speed 100 duplex full int G1/G1/1 speed 100 duplex full. All right, so let's see if we can get this fixed. Now we got to go up to R1 and do this, all R1 and everything. They should be there. R3 should eventually go to running that. So let's go to R3 and see if we can get the int. We can do this int G001 no negotiation. It says speed 100. Okay. No. Auto. No. Do show run. I can't remember what the command is. Sorry, y'all. They got an automatic negotiation auto. Okay, so we do no negotiation. Negotiation. Wow, still. Negotiation auto. Auto. No negotiation. Auto. Speed 100. Duplex full. Go back to R1. Let's go to do show. Oh, no. Show IP and brief. And okay, so let's do T. Int G001.1. No negotiation. I have it there. Oh, I bet it's on the main interface. Int G0. No negotiation. Speed 100. Duplex. All right. So now we should get now. If I do a show int G00001, we're hopefully going to be running at 100 megabits per second. Yep, full duplex 100. Now let's check our links. Should be all the way up here. Okay, and it's still trying to figure out what's going on. Hopefully it will eventually clear itself up and we'll get all of our information. Right now it should be running dual, trying to figure out what in the world is happening, because it's got no adjacency. All right, there we go. All right, by forcing all the speeds to be 100 across the board, I am now able to match the topology table and the information that's in here. The numbers are different, but the actual table is correct. So you'll see now 23.0 has one successor and one feasible successor, which is here. We have two successors, so in other words, we have two equal cost passed to the 3.0 network. And that was all because the speed on the interfaces were incorrect. This is an excellent example for you for the real world. It is going to do exactly what it is supposed to do using the speed of the links to determine the metrics. If for some reason the speed of the link is wrong for whatever reason, in our case, it's because those gigabit links are connected in the back end to a fast Ethernet switch and cannot actually run at a gigabit. Even though they look like they're gigabit, they're not. That could cause you some serious issues in your routing, because it could be that you actually have 4 or 5 routers connected together with their Ethernet, their gigabit Ethernet, thinking it's going to be gigabit, but because you plugged them into a switch that's a fast Ethernet switch, it won't work. So be aware of those types of issues. That's the kind of thing you need to be able to drill down and troubleshoot on to find out why routes are not correct. Now, the rest of this is literally just going in and configuring passive interfaces, setting up authentication, those types of things on each one of these. So here's your authentication. So setting up either on the interfaces itself or inside of named configuration mode. So do notice that's one of the nice things about named configuration mode. You don't have to go out to every single interface and put things. You can put it on the interfaces underneath the named configuration mode. So it's easier to work with. And everything's in one place instead of being spread out across your different areas. The other thing we mentioned in here is variance, and that is unequal cost load balancing. You'll notice here that with this particular example, we have 2 different routes, but those 2 routes are not load balancing because they don't meet the feasibility condition. It is possible to actually go in and create the variance, change bandwidth, and then do variance and set it up to where it will load balance across 2 links that are within a certain variance or difference of one another. Now, be aware that's not the greatest thing you want to do, because then you're not actually load balancing across equal cost paths. you're now load balancing across unequal cost paths. And that is something that EIGRP can do that OSPF cannot do. OSPF can only load balance across equal cost paths. But EIGRP can do the opposite. It has the ability to do unequal cost. All right. So just wanted to show you that as an example of how we can have some issues. You want to know your command show IP EIGRP interfaces. And you also want to know, again, show IP EIGRP neighbors so you can see the neighbors, how long it's been there. Here's the installed routes. Show IP route EIGRP will show you just your EIGRP routes. Why do you think the D is used for EIGRP?
Dual.
Exactly. That's exactly right. Because it's running the dual algorithm. A lot of people wonder why it's not E, but it's D for the dual algorithm. All right. And if you see an EX, it means an external route. So it's a route that's been brought into EIGRP from an external source. Router ID, we talked about that. Now, what is a passive interface? By default, an EIGRP router will send out looking for its neighbor every X number of seconds, depending on what speed the link happens to be. If you don't want it to do that, you've set an interface to be passive. And you would want to do this on any interface that doesn't have another router on it. And it's not going to be participating in the EIGRP environment. So you can put passive interface on a particular interface, or you can go in and say passive interface default, and then do no passive interface for individual interfaces. Realize that if you do passive interface default, it will break everything until you do no passive interface. Again, it's possible to do in named mode. You just do it inside of the named configuration. So AF interface default, passive interface, and then do AF interface. So address family interface. So you're underneath the address family, gig 01, and it will tell it not to let gig 01 be passive. Not gonna spend a lot of time on authentication. It's basically a good, it's a good idea to do authentication to make sure someone can't drop a router into your network and just start participating. Spend a few minutes talking about the EIGRP metric calculation. By default, we have 5K values. And these 5K values all really come down to two things. And can anybody remember what the actual bandwidth or what the actual metric inside of EIGRP ends up being computed?
Bandwidth and delay.
Bandwidth plus the sum of the delays. Okay, so it's bandwidth plus the sum of the delays in microseconds across the links. So all these other K values drop out other than bandwidth and the sum of the delays. You have to be careful though. Again, if you're not using wide metrics, anything above 10 gigabits will be exactly the same speed, or will look the same metric wise. So this is the classic metric. You'll notice as we get above anything faster than 10 gigabit, it's going to all be the same metric of 512. That's why they introduced wide metrics. And wide metrics basically just takes composite metric and increases it using a K6 value. Notice, by the way, if you're shown any type of bandwidth calculation for EIGRP and you see K6 mentioned, if K6 is in here, it's using wide metrics. So if you see anything in a calculation on a question and they're asking you which type of metric is being used, wide or classic, if you see K6, that is an indicator you're using wide metrics. Okay, and that is what is used to make that extension for the composite metric, to basically take it times 256. Okay, so we can get speeds up to, I was wrong, I thought it was 455, it's 655 terabits per second without any scalability issues with the wide metric. So if we scale it to 256, we are able to, we scale it up to 65,535, which is where we go from 256, because actually EIGRP was scaled for 256 above IGRP. And then to get wide metrics, we scale up 65,535, and that gives us the ability to go up to 655 terabytes. I think we'll be okay for a while with that. It's not going to be a big problem. You can use backwards compatibility because the unscaled bandwidth, you can just take it and take the bandwidth plus classic scale and then divide it by the scale. The problem is if you pass through a mixture of classic and wide metrics, you can end up with really weird metrics. So either use all classic or use all named, so that you're using all wide or all standard classic. Okay. And I would go ahead and tell you just use all named configurations in the real world for that reason. Okay. You can set your own K values. You're only going to do that in very extenuating circumstances. Basically, when Cisco says, hey, do this. But you probably are not going to play with those K values in the real world very much. Have any of you ever seen anybody mess with the K values other than just in a lab environment? Because I really haven't. I hadn't read anywhere anything about changing K values. Okay. And then load balancing, again, maximum pass. By default, you can set a maximum number of pass if you want of 6 or whatever you want to set it to. I think the maximum is 8 for EIGRP, if I'm not mistaken. But load balancing, if you don't want it to be equal cost, you can do unequal cost load balancing. And you can do that by taking your feasible successor route and dividing it by your successor route. And then that will give you the variance you'll need for that feasible successor to also be used. So that basically means round, the pipes up, by the way, mean round up. So if you take the successor, feasible successor, divided by the successor, you would need a variance of 1.6 or 2 in order for a feasible successor with these numbers to actually be used as an equal cost or an unequal cost load balance. I don't really see how useful this would be. I don't think it's a good idea because you're basically not using your fastest link. And so I would do my best to try to get equal cost pass and do equal cost load balancing. Now, folks, that's EIGRP in a nutshell. Any questions on that? Any questions on my example where I showed you what we had to do to fix this and why that issue was taking place in lab 212? If you run into another lab and you're having a similar situation and values are not matching, you can always go in and do what I just did here, which is go to each one of these links down here, because all this R1 is directly connected to D1's gig 1011. And G101 is in fact connected with a crossover cable to D2's G101. So the links down here are all true gigabit links. The links from R1 to R2 and R2 to R3 are not. These are going to be fast Ethernet links because of the fact we've got a control switch in here that's fast Ethernet. We'll try to replace that, but I don't think it's going to happen before this class is over at the end of the semester because we'd have to take the pods down to do it, and I don't want to do that because I'd be offline for you. But be aware, you can always just change the speeds in here, across here, and here to 100 megabits, and then everything's going to match. All right? Any questions on today's discussion of EIGRP? Any questions, anything to do with the class so far? Okay, everybody, I'm going to stop the recording.